Okay, so in terms of the content that I intend to cover, I want to mention maybe one or two more things. Hopefully, this lecture and one more, then I will be through with the content that I want us to cover, and then we will now concentrate on getting your assignment progressing. So I'm proposing this morning that I just delve into these extra thoughts that I want to share with you to add on to what you already have, and then so that maybe this session and the next session, then we can now fully concentrate on the assignment. So just as a recap, we did make a small discussion on shear walls in the previous sessions. We sort of just laid the thought of the sense of the shear wall in terms of numbers. We saw that the shear wall basically is an element that is very stiff in a particular direction, not necessarily because it has a larger cross-sectional area, but because of the way the material is arranged. So we looked at this illustration of a square versus rectangular element, and we pushed that thought a bit further to say, now if the column we are looking at in our hypothetical building, the 800 by 800, if we were to rearrange that column into 200 by 200, then it become a wall. And we saw that the second moment of area, which we said is a measure of the stiffness, of the bending stiffness of an element, becomes almost 16 times. Comes almost 16 times. So that is we saw that is the thought of the shear wall. We also went ahead to make an attempt to say why when shear walls are properly and adequately provided, then shear walls are able to carry basically all the lateral load that would be in a building. And most standards, we said, allow the designer to basically load 100% of the lateral load onto a shear wall, and to design the shear wall to carry 100% of that lateral load. We also did mention that this is not absolutely correct, but because the shear wall is a lot stiffer than the other vertical elements in a building, vertical load carrying elements in a building, then because of the much bigger stiffness, it carries the bulk of the loading. I also did mention that there are many models that have been proposed, or many thoughts that have been shared about how load will be distributed to these vertical elements. And I mentioned that amongst the pioneers of this work is two gentlemen who were professors. One was called Muto, the other one was called Stodola. and they did an excellent job just to start us off in the direction of story stiffnesses and how we would calculate those, including the center of action of those story stiffnesses and how each element would carry how much in terms of the share of the lateral loads. It's very interesting theories, though they are out of the scope of this course, so it's just sufficient to mention here that these do exist. If somebody is really interested in that level of analysis, then that's a good place to start from. Then now come up this way towards the present to see what others have suggested in terms of refining that. Again, this science of lateral loads, especially earthquakes, is even wind and how they're carried in buildings is of great interest, and the knowledge is extremely dynamic. That every day new thoughts that are more refined are shared. As we speak, there is enough fellows who are doing higher degrees research on this one, masters and PhDs and stuff like that, all over the world. So this is a subject that is still growing, and it's really interesting. Now we also came to a point where we said, so how do we analyze the shear wall? And we said we idealize it as a vertical cantilever. Now, for it to be a vertical cantilever, it has to be fixed at the bottom, so to have a fixed support. So we say we fix it, we load it, we analyze it, and then we design it. We said two important items in the design is that we have to ensure that the wall is able to take the bending moment in its cross section. We said there are few approaches to different standards have got different ways of how that is designed. And then we also said that the foundation has to be designed for both the axial load, courtesy of that wall, vertical reaction, and the bending reaction as well. Now that is shear. So what do we do with the columns? That's what I want us to discuss today. What do we do with the columns? How do we support them? And to answer this question, maybe not to answer it, but to just give you thoughts so that you can consider when you make a decision, what kind of support do you use? I want us to make a discussion on that today. So please remind me that we still have to discuss about where we fix the base of the building, or where we fix the base of the. Maybe we will discuss that in the next lecture. So consider these two frames. Pages. We only have one page here left. Let's try and squeeze the information there. Let me create another file that has a bit more space so that we don't get stuck. Yeah. I think we scribble on this one. Put today's date is 1st of November. So 01, 01. There we go. Starting to misbehave this thing. 01. November 2023. So consider these two frames. Put a frame here. I've got another frame, same dimensions. It's just a beam and a series of columns. Let this frame be fixed. The columns on this frame be fixed at the bottom. Let this frame have columns that are pinned at the bottom. We can label this to say this is fixed foundations. And this is a pinned foundation. Let me move this writing a bit so that we can put some bit more detail here. Let's put it down. Fixed foundation. Sorry. Fixed foundation. Picked foundation. Let both of them be loaded with a lateral load, like what we have been calculating. And that will be a lateral load on the frame. Say lateral load, lateral. On the frame. Lateral load. On the frame. Courtesy of this lateral load from analysis of structures, we know that the column will have bending moments in this manner. If we were to analyze for this That's a bad line. We're to analyze for this lateral load. This frame will have bending moments. Why is it that it wants to be biased there? It's got to be a bit reasonable. Yeah. The column will have bending moments in that manner. Because it is fixed, we will have a bending moment at the foundation. Because it is fixed, the analysis will allow us to load some bending moments there. The frame that is pinned at the support, at the columns are pinned at the foundation, the bending moment will be like this, with 0 moment going to the foundation, to look like this. Okay. And the beams will have a bending moment that looks like this. That's a bad line. Bending moments like that on the beams. Bending moments on beams. Bending moments on columns. Okay. The first important thing you want to take note of is that because we assumed this frame to be fixed, because we assumed that this frame was fixed at the support, it's important to note that bending moments will be generated at that support due to the fixity. Right here, notice that a moment is generated here due to the fixity. Here due to the fixity. You also notice that no moment generated here because it's support. Okay. Now, what does this imply in terms of the rigidity of the structure, in terms of now the kind of foundations we need to do? Because this frame is fixed, this frame is stiffer. frame is stiffer, is more rigid. Because it is fixed, it is stiffer, it is more rigid. And in terms of physical terms, the implication of that is that because some bending moment is resisted at the foundation, less bending moment therefore needs to be carried by the rest of the frame. I'll repeat, because some bending moment is resisted at the foundation, whatever is left to be carried by the frame is slightly less, meaning that you wind up with a slightly lighter structure. You wind up with a slightly lighter structure because the foundation is stiff, so it carries some of, it actually contributes to the resistance of the sway, that lateral force. The foundation contributes to the resistance of the sway, so the frame itself does not need to carry 100% of that effort to resist the sway. So you wind up with a slightly lighter frame. So that's an advantage for this fixed foundation, if you can achieve it. If you think about the pinned foundation in the light of this thought, therefore, the pinned foundation is more flexible. So the rest of the frame is left to fully carry the resistance, or to generate the resistance for the lateral force that is being applied. So you wind up with a slightly heavier frame. You wind up with a slightly heavier frame. So we will write some notes towards that thought. And I want to draw a line here at the center so that we sort of write some form of comparison. So draw a line here with a separation. Yeah, approximately at the center like that. So we have said the fixed frame is more rigid. Is stiffer at the foundation. Thus, the members of the frame that is the beams and columns tend to carry less member forces. Okay. On the other hand, we've also said the pinned frame less rigid. It's more flexible. At the foundation, thus the members of the frame that is the beams and columns tend to carry less member forces. No, not less, more member forces, sorry. Tend to carry more member forces. More is not a good word, bigger member forces. Larger is a better word. Member forces. So that's definitely an advantage to the fixed foundation for the column. If we fix the column at the foundation, while we slightly lighter member forces up at the top. Okay, so how much lighter is also a big variable, depending on the relative size of the building. Not relative size, but depending on the size of the building. How many floors and things like that. At some point, as the building becomes bigger, at some point, fixing or not fixing does not have much difference. I'll repeat. This advantage depends on the size of the building, and as the building becomes bigger, at some point this advantage vanishes. It's almost negligible. So what does that mean to the foundation? So right here, implication to the foundation. Implication to the foundation. So from your foundation engineering or geotechnical engineering, you are aware of this. Let me just redraw this for the purpose of this discussion. This one you have learned and you have mastered. If you have a foundation, like that, in a column, bad line, this one here, carrying a column. That column is carrying an axial load, carrying a bending moment, either bending moment applied on the column or due to the eccentricity of the column to the foundation. Now in this case, the second thought is not there. We are just transferring a bending moment from the column, what we have sketched up here, this one here. We have a column that has got an axial and it's also bending. So that's the situation that we have. So we know, courtesy of that load P, let's call this M. Courtesy of that load P, we will have a uniform pressure below the foundation. Courtesy of the bending moment, we will have a moment that does that, a pressure that does that. And if you add these two, find you have a pressure diagram. It could be that way. Depending on the relative on the relative magnitude of the force P to the moment M. If the moment is bigger, then you could even have, in a worst case scenario, something like that. You could have that. If the moment is significant compared to the axial. So it's a whole variable. I'm sure you've mastered this this kind of foundation. You must have been taught in your foundation engineering, geotechnical engineering. Now, this stress concentration here is undesirable. And many times cause problems with both at the design stage and in the service. I like to say could cause problems. Could cause. So you can say could causes, so you say could cause problems. Cause problems. Life of a structure. Life of the structure. Due to, okay, let me stop that sentence there. Probably when you went through the course on foundations engineering or geotechnical engineering, when you discuss this, it might have been mentioned that that stress concentration is undesirable. But also, just to further this thought, that negative pressure up here is also undesirable. This negative pressure makes the foundation inefficient. Makes the foundation inefficient. I'll leave that at that point so that we don't dig into that. You have, I'm sure you have gone through this extensively with the experts of this area. But just a thought. So now, you see, when we do the foundation, we want to ensure that it doesn't exceed the safe ground bearing pressure. So usually where you have this stress concentration, there's a very high probability that you wind up having that stress there exceeding the safe ground bearing pressure. In physical terms, what that means is that when this structure is put up with that size of foundation, then that area will deform too much, because the stress applied is exceeding the capacity, maximum capacity of the ground there, in terms of resistance of applied stresses. Sorry. So you don't want to do that. And if you now, to avoid this, if you have this kind of scenario, most of the times you find that you need to increase the size of the foundation. You need to increase the size of foundation to avoid this kind of scenario. I think those who might, if I'll get an opportunity to take you through these are course on bridge design. Maybe I might mention, I might show you how just the increasing the size of foundation varies this you're able to play with the value of that maximum stress, but just changing the size of foundation of this element that is carrying axial and that. Okay. So that is that foundation. This other foundation, come back to it. So you got same foundation, or similar, not same but similar. So let's put here, we got foundation and it's carrying a column there. Now, in this case, just as we have seen here, we don't have a moment. They only have the axial from the column. So you've got an axial force here that goes into, and the result is a uniform pressure distribution below the foundation. We see this stress block. Let me just use the same color. This stress block is more desirable. For the foundation, sorry, due to its ease of design, and also avoidance stress concentrations. So these are the thoughts that go into a foundation. Now, with these thoughts, therefore, you will find that a lot of designers, and I'm not saying all designers, a lot of designers, they prefer to work with this foundation as opposed to this foundation. So it's a preference thing, but it's not cast in stone. And when you are designing and you are aware of what advantages you get from this side and from the other side, then you're able to make your own engineering judgment as per the problem at hand. So we will not say that no, this is better or the other one is better, but these are the thoughts that go into these two possibilities of supporting the column at the foundation. Many designers, they prefer to just make it pinned. That way, then you have a slightly heavier structure, so you design for that, you provide for that, as opposed to having to then design for this and to deal with the extra effort of dealing with with the stress concentrations. I will conclude this session before I allow you to respond to these thoughts. I'll conclude this discussion by writing this statement here to say that the way you model a structure in analysis is approximately the way it will behave in real life. So write this statement, I'll leave this statement here for you to think about. That the way you model structure in analysis approximately the way it will behave in real life. Why I'm writing that there is to say, if in your analysis you model that foundation as fixed, the analysis will send some moments to that foundation, which then you will need to design for. So the structure becomes stiff by design at the foundation. And when it is loaded, it actually sends some moments or some bending moments to that foundation. If you model your structure as pinned in analysis, what will happen is that you will get 0 moments at the support. In theory, when you design the structure, you will not then design that support to carry any moments. Now, we know that this is not absolutely true because the nature of concrete and how it is reinforced, it is next to impossible to have a pin, perfect pin. But it will not be designed to carry moments. So in real life, when the structure is loaded, that point will be weak. So when it tries to send moments there, it will just basically deform. It will not be able to resist the moment. So no much meaningful moment will be generated there. And therefore, this structure will still behave in real life as if it was pinned at that point or approximately pinned. That's why I'm writing this statement. And we could go on and on with this discussion and look at beams and how we analyze them and design them, and eventually they behave as the way we have analyzed and designed. We could go on and on about this. I want to tie that thought to something we started with much earlier in this unit. No, not this unit. So I will not talk about it. It's not in this unit. I'm getting confused. But this is an important statement, and we could make a discussion on it for a few more minutes. But I want to leave it at that point, and I want to allow you, ladies and gentlemen, if somebody might have a thought or a question or an idea about these thoughts that I have shared here in these few minutes, please, you can raise those before we wind up this session. Any question, any suggestion, any challenge to these thoughts? Yes, sir, this is Kagonye. Please go ahead.
So when you're doing RC construction, is there a way of making them either fixed or pinned?
Yes. And I was careful to mention that it's difficult to achieve a perfect pin, but you can actually design the element to behave as if it's a pin. And because you've asked that question, I'll push these thoughts that I was sharing with you a bit further, just a bit further. To respond to that, I was hoping nobody would ask that, but now that somebody's asked, let me just. If you have a beam, a reinforced concrete beam, consider the beam scenario below. So let's look at 2 simple beams. One is fixed and one is pinned. simply supported. Okay, so they've got the same length, L. Yeah. And same loading, W. The bending moment diagram for this one will be something like that. The bending moment diagram for this one will be something like that. Okay. So if you assume this beam was fixed, like in the first case, then when you come to design this beam and detail it, you will make provision for reinforcement there to take care of that. And you will make provision for reinforcement there and there, not minimum, to take care of that. So in real life, this beam will actually behave as if it was fixed. Why? Because you've made those provisions. The other beam, if you look at it, you will make provision here to carry that moment. Then you will provide minimum here. So in real life, this beam, if it was to try and behave as if it was fixed and it tried to send some moments there, because you know what will happen is that the moment doesn't, the free moment doesn't change it. So it will try to do that. If it tried to do that, it will find that there is no capacity to carry that moment. I hope that makes sense. So it will simply go back there and follow that. So it will load the center first to its capacity before it tries to send something there, because there is no capacity there. You have not provided capacity. This is a thought that informs this sentence, and maybe we might not be able to fully soak in this thought now, but as you go along and you think about it, it will start making sense. This is similar. No, let me pause it at that point. But when you talk about steel structures and you talk about continuous construction and simple construction, it's the same thought. If you assume it's continuous, it will send moments to the supports, which you'll need to then design for. If you assume it's simply supported, it will not send moments to the supports, but it will send moments to the span. So you'll have a bigger moment there. So you wind up with a stiffer element there. And we can go on and talk about the deformations and how these even the deformations will cause the structure to behave the way it was assumed. But so that we don't lose focus of the content that we just discussed above, I think I want to leave it at this point. I hope that helps a bit. It's a thought that you want to sit with it and soak a bit before it makes sense. I hope that helps a bit.
Yeah, it helps.
Good. Any other person we could have, maybe one or two more, and then we close this meeting. Yes, Anthony.
Yes, this from previous discussions on the earthquake forces calculations.
Yes.
Yeah, I noticed that the forces per story were increasing as you move up. So is it true that the top story should be carrying a much more load compared to...
Very good question. Very good question. Very good. And I thought somebody would ask that question. You know, Let me stop sharing this. So we have an earthquake base shear, which we have distributed, right? And seemingly, that flow, say it's loaded by 200, then 150, and then 100 going downwards, right? I'm talking to you.
Yes, yes.
Now, you know, when we come to, if we have, let me sketch it. It will be easier to follow. Let me sketch it. But I think that's a very good question. And now you can switch off your mic, Anthony. Okay, good. So let me write here aside. So you got this building. You got this building. It's got okay, so something like that. We got here, say 100. Here we've got 80. Here we've got 60. Here we've got 50. Here we've got 40. Here we've got 30. That's what you're asking. Now,
Yeah.
this is the number that goes onto that flow. Okay? If you think about it, if you isolated a free body diagram, say here. If you isolated a free body diagram here, if you were to cut there, and you were to be left with the upper frame. Okay. And you have to deal with this force here. So that's 100, that's 80, that's 60, that's 50. Okay. Can you tell me the value of the shear force that is being resisted here? From your analysis of structures. Sum of forces in the x direction. I'll tell you. I mean, sum of forces in the x direction. You've got 100 plus 80 plus 60 plus 50. 180, 240, 290. So at any level that you consider, the total shear that is being resisted by that level is actually increases because it's cumulative from the top going downwards. Are you able to see that, Anthony?
Yeah.
Does that answer your question?
No, a bit, because from the calculation we were allocating some force to the top story using some equation. So it happened that from that equation the force was 28 kilonewton.
Yes.
The top story, the 18th story. Yet the 17th story was about 200, 100 going down.
Yeah, that's okay.
So the top story can carry a
that's
load.
in order. It doesn't have to be. You see, that whip effect. It doesn't necessarily mean that the top story has to have the highest force. In fact, the standard that we were looking at, put a limit to say this force does not need to be more than 15% of the total force of the building, on the building. So it's not necessarily that it is the biggest force, not necessarily. But we're saying in some situations it could be a significant force, probably more than what would have been allocated there.
All right. Thank you.
Okay, but in actual fact, as you go down, the shear that needs to be resisted by every level increases. So you find that if you're checking the total amount of shear, because the total amount of shear at any level is all the lateral above that, all the lateral applied above that. So it goes on increasing. It's cumulative as you go down. So that when you get to the foundation, you get the cumulative is actually the base shear. It's a sum of all this that you have distributed. So it's the base shear. When you go to the first floor, is the base shear less just the force on the first floor. When you go to the second floor, is the base shear less the first and second floor. So it goes reducing until the top. So if you think that if you can understand that it goes accumulating, then it's actually not reducing, it's increasing. Any other thought that somebody has? We absolutely need to now conclude this meeting. Okay, thank you. So I think I have maybe just... Yes, Fanuel, yes, go ahead, please.
Morning, Professor.
Good morning. How are you, sir?
I'm requesting if we can... I'm fine. We are requesting if we can represent the BTech group.
Okay. So
assignment, yes.
Let's discuss this a bit separately, because the BTech groups, we allow them to be visitors into this class, But yes, okay. I think it's something that between yourselves and myself we can organize. I don't think it's an impossibility, but let's discuss this out of this meeting. Sawa Fanuel.
Yes.
Good. So thank you. Allow me to stop at this point now. Yes, Mutero.
When it comes to the shear wall, are they designed to carry any lateral, not lateral, but axial loads?
Yes. You see, because the shear wall is part of the building, so it is tied to. Okay, how do I explain this easily? The shear wall is actually a column that is optimized to carry lateral load. That's where we started from, if you can remember. And we said if we have a column and we just elongate it so that we achieve a bigger stiffness in a certain direction. So it being a column, if you think about it, it is because it's supporting some part of slab. So the slab will load onto it. Okay, so you need to check for that. But you find that the axial load that goes onto the shear wall, because it's such a large element, almost linear element, the axial load is usually not the governing factor for the design of the shear wall. What would cause the shear wall to have problems, maybe to fail or something, would actually be the bending moments. That's why we've talked about the bending moments. But you can check. Is like this question, Muiga, is similar to the question of, do we need to check slabs for shear at the supports? You see, when we design a beam, we check bending and shear. So why don't we check the slab for shear at the supports? We only do bending. It's because, yes, the shear does exist there, but the slab, the area that is carrying the shear, is so big that you can check it. I mean, nobody refuses you to check, but it's almost granted that you will not have a problem. The only problem you will have is if you have a concentrated load on a slab, then you check for punching shear. So similarly, this shear wall actually does carry axial load because there are slabs connected to it. So it carries axial load, but the governing criteria would be bending and shear. Okay, even the shear, it's just a check, because it's a very large area that is resisting the shear. So you find that you just check for shear. Rarely do you have a problem if the wall is adequately designed or adequately sized in terms of shear. So you check, you first design the wall to carry the bending. If it carries the bending and you're comfortable, then you can check these other things, and most probably they will be adequate. If the bending is not adequate, then you don't have a shear wall. If you start with, for example, checking the shear and then checking the axial, it is possible that you find that they are okay, but then the bending doesn't, because bending is the critical. So we start with the bending on the shear wall, and then we check these other things.
All right, thanks.
Good. Great. So thank you, ladies and gentlemen. Have a good morning. Let's meet again in the next session and continue this discussion. Thank you.